Hello. Another day, a pretty exciting day today because we are meeting with Ash, the creator of many programming tools.
And a company.
And a company called Unum. We'll be doing an interview with him. Super knowledgeable person.
Very smart. Very low level.
Very low level, C++, C.
It will be something completely different to what you saw previously on our channel, I guess.
Yeah, I'm hoping for the interview to be super specific, super low level. We met Ash at the Open Source AI Day in Berkeley. Sunday. His talk was amazing. One of the best talks I watched. I've seen
one of the best of the 2 talks you've seen.
I've seen a couple of talks, but this talk was one of the best. And I'm looking forward to it. So
me too.
Stay tuned and see you
in a bit.
Welcome, Ash. It's a pleasure to have you here today. Thanks for agreeing for this interview and to share your perspective on AI in general. So we met like a couple of days ago on Sunday in Berkeley. There was this event called Open Source AI. I was watching your talk and I was kind of blown away. It was, in my opinion, one of the best talk. I've only seen a couple, but yours was pretty great.
One of the top 2 talks of the 2 talks you watched,
exactly,
right?
One of the 2 talks I watched.
That's the best compliment I can get. Okay, I'll take it.
So there is a lot of interesting things, a lot of fascinating projects you are working on. But before we dive into that, maybe you could tell us a little bit about yourself, about your journey, about your story. How did you start with programming? And then how you transitioned to AI, if maybe you started from AI from the get-go. But
So I started programming maybe close to 20 years ago. And I think it's not a good idea to cover all 20 years. In short, I did a little bit of like just basic educational programming and just like learning the fundamentals of computer science. Then in my middle school years, I got to do some web development and freelancing and like learning how to work on your own, be an indie developer. One thing after another, I got myself into the Apple ecosystem with the 2009 aluminum body MacBook Pro 13-inch.
The first one.
Yeah, I remember it as if it was yesterday, my first expensive tech purchase. And then I started developing iOS apps. Yeah, I did it for a few years. Then I left programming. I was at the very peak of the Dunning-Kruger effect when you think you know everything. And I tried to explore something else outside of just computer science. So I spent a few years doing physics and studying it. And then I left to start this project that I'm still building called Unum, which was 8.5 years ago when I realized that I need to devote my life to building towards AGI and helping the world with AI infra. And I decided to leave my passion, which is science, in favor of another passion, which is computing. So here I am.
Interesting. On your website, you are saying that you are a CS researcher without publications, which is pretty funny.
Yeah. Love it. Well, actually, I tend to think about this a lot, how the educational system is built, as some of my first most successful applications were in education. The period when I spent in the university and in academia was one of the happiest periods of my life. And it was very encouraging and fulfilling and intellectually stimulating. But in reality, I started reading more papers when I left academia. So in the university, I would at best read like 1 or 2 papers a week and like properly understand it. And then when I started this project, for a couple of years, I would skim through maybe over 1,000 papers a year. Wow. So it's like on average 3 a day. And you do it for a few years and you attend several conferences like every month or so. And one thing after another, you kind of start feeling the tech. You don't even like have to read every paper, you just kind of know what it is about.
Interesting. It's kind of similar for me, but not that extreme. I was just, but the same feeling that during the studies, I haven't been like into reading papers, but after I just started to searching certain informations, like a specific topic and how to solve a problem.
Researching very deep.
Yeah.
And the structure of academia kind of stimulates people towards publishing a lot. Yeah. I'm not sure that's the incentive I like, and I don't want to kind of be part of it. Mm-hmm. So the way I think about it for myself, I really enjoy reading papers, but if I were to write, I would probably limit my career to just a couple of papers, right. And I would try to make them extremely short, but fundamental, so that the ideas would apply outside of the original intended application and be broader. That's the end goal.
Absolutely.
But you've mentioned that the company.
Yeah.
What it's called? Unum? Is this the right pronunciation? Unum?
So Unum, I'm not sure what's the right way to pronounce because it's a Latin word, and not many people like really speak Latin, and the language is shaped by speakers, not by old textbooks. But yeah, I assume Unum is the way to go.
Unum. Okay. And you said you started working on it like 8 years ago, and it was related to AI.
Yeah.
AI 8 years ago. It sounds almost
Yes.
like a science fiction story.
You're true there. Like, we were not taken seriously for a very long time. And you see all kinds of friction from peers, from other founders, from people in academia. The way I thought about that is AI in midterm would require a lot of data processing. And it just so happened that I was very deep into computer science, both the algorithmic side of things, but I also liked writing high-performance kernels. And when you do science, you occasionally have to implement like computational kernels, simulations in CUDA, sometimes kernels in Fortran, that kind of stuff. We talked briefly about that. So I thought I can put my skills to a good use and optimize all the infrastructure that people are going to need in the next few years to build smarter, more intelligent applications. So I kind of went from this application layer where I developed a lot of the iOS ecosystem-related things down a bit, finding the shared common denominator between all those dozens of apps that I was implementing, finding maybe like the 4 or 5 core libraries that the world needs really well implemented so that the next wave of applications can be smarter, more scalable, intelligent. You pick your word.
I was kind of blown away when I was watching your talk that you are so focused on performance. So Unum consists of several, let's say, modules, right?
Yes.
And maybe we could go each by one, like discuss each of those modules separately. So there is USearch, UForm, UCall, and UStore, right?
Yes.
And the idea is to combine, to provide some layer of abstraction. Can I use this word? To do certain operations.
Yeah.
But the end goal is to, as you say, make searching for AI more performant. Is that a good way of?
That's one angle. So when we look at the modern data stack and a lot of the existing cloud companies, they really love building this monolith vision. Like, this is our product, or this is our platform. Use it or don't. You can pick any other one.
Gotcha.
In the way I generally write software, I try to find optimal ways to cut it into separate projects. It's very hard for me to guarantee at any given point in time that every project is state-of-the-art in its own way. But if you're passionate enough, you can just take the parts that you think are good enough and replace the parts that you don't like with other components, maybe not the ones that I wrote, maybe alternatives, and have a better option. So I think one of the beautiful things about software, it can be very modular. One of the beautiful things about open source, it encourages innovation and people kind of learning from each other, forking each other's work. And I guess one of my biggest mistakes as a programmer was I learned a lot from open source, and I waited too long to start contributing back. And I guess many people have the same opinion. Now that I'm doing it, it's very fulfilling. And every day we see people coming in from different parts of the world and sharing their feedback, occasionally bringing in great ideas, sometimes sharing their patches to this global vision that consists of separate, smaller libraries. Most of them would never use all 4 or maybe the other 5 to 10 that we have internally and haven't polished it to a mature stage yet. Sometimes they would just use USearch that you've mentioned. It's probably one of the most popular ones at this point. And I guess we can unpack every one of them.
We should do that.
Yeah, but what you mentioned, the modularity, it resonates with me because of the Unix approach. Right?
Yeah.
I think that's with
Exactly. I love Unix philosophy, let's say, that stacking things or small things that do one thing pretty well. I wanted to ask you, because during your talk, you were talking about taking this fast API application, it was a REST app API or something like that, and you observed that it's relatively slow, right?
Yeah.
And then you just added one module you created, UCall, right?
Yes.
And you made it like 70 times faster or something like that?
The RPC layer, right?
Yeah.
Yes. So that's actually an interesting place to pause for a second. So people think about computers as things that compute, hence the name. So number crunching, performing like all kinds of numerical operations. In those places, efficiency is very important, but you don't always feel the cost of abstractions because like if you're in a compiled language, your code still translates from the higher level language into assembly, and then the CPU just executes your assembly. In IO-intensive applications, as opposed to compute-intensive applications, the cost of abstractions is much easier to trace. So we kind of deal with those like multi-layer systems that accumulate complexity and reduce throughput at every layer. So when we go through a computer science course, we have this networking diagram shown to us. I actually never been to a computer science course, but I assume that's what people do. They have like maybe 7 layers of the TCP/IP stack, and then every one of them has constraints on the length of the packet, on its structure, and every layer performs its operations of unpacking, parsing, decrypting. So when you just look at this, you realize, oh wow, there are so many ways you can mess this up. There's so many ways one bad design decision here in one specific operating system kernel will end up killing all of my application's performance. And then after that, I will have to start thinking about horizontal scaling. So I suddenly cannot sustain my users on one machine. I need like 10 machines. And I need a load balancer in front of them. I need a proxy. I need a separate layer of like certificate verification or something like that. And we started producing and multiplying complexity over the last 20 years of computing ecosystem without ever going back and asking ourselves, like, do we really need all those 7 layers of the TCP/IP stack? Or would it be wiser to, let's say, clamp all of it into like a quick QUIK, like a HTTP 3 standard-like thing? In the case of UCall, I designed a remote procedure call library that is not going as far. So I didn't even have to implement Quick or design it. All I did, I took a recent interface from the Linux kernel called IOUring, which allows me to avoid system calls and implement asynchrony more efficiently. And then instead of separately implementing a Python server layer and a Python application, I kind of implemented all of this as a library that has a Python SDK. I removed maybe like 4 or 5 different layers of abstraction. And yes,
pretty cool.
A 70x throughput improvement, even on a single CPU core, is definitely possible.
It sounds like a low-hanging fruit in a way, right?
I'm not sure. When you describe it, it does sound like it.
Yeah.
It is once you know what you're doing. And as a community, I think we should find ways to encourage more of this. So occasionally when I do this kind of stuff, the original implementation may take only 2 days. And there's plenty of engineers who might be interested in this, but they are not always like encouraged to try. Of course, the first time you do it, it may not take 2 days. So the example that I generally refer to would be either database engines or matrix multiplications, because I wrote a lot of those. So the last database engine I wrote was my 8th database engine. And every single one of them takes less and less time to develop. So the first time it may take me a few months, then it's a few weeks, and then every iteration is less than a week.
Because you already have this context, right? You already know how the path from the beginning to the end, and then you could just add a new information on top of that.
And same was like with web development and application development a decade ago. I remember that when I was developing some of my first apps, of course I would do dumb mistakes, like you switch from one programming language to another, and let's say even indexing sequential data structures can be from 0 or 1. Yes, there are languages that do it from 1, and they're still in use today, and I would make those stupid mistakes, and every little app would take me months to develop. But once you get the sense of it, every following experiment is lighter and easier.
Pretty interesting.
I'm wondering, because we are another product of yours, we are huge fans of SQLite.
Okay.
And we love using SQLite. We are fans of it before it became popular. We were fans of it before some people suggested it could be used on the edge and easily replicated. So what's your take on SQLite?
I think, okay, so I think I will be quoting some people this time. The quote that comes up to mind now is, I think Bjarne Stroustrup, the author of C++, said there's languages that people like and the languages that people use. And maybe like to a certain extent, SQLite fits kind of this description, even though of course it's not a language. So I personally have very strong opinions on a lot of computing related topics, especially storage. And I believe that storage today can be done much more efficiently than any single database does, including SQLite, of course. But it would be foolish not to say that SQLite stood the test of time better than practically almost any piece of software written. SQLite works like a charm on Macintosh, on Linux. You can make it work on Windows, even though compiling it as a library is not always easy.
You don't need a server, right?
Yeah, you don't need a server, and that's actually a very important distinction. Like, even when you talk to people in the Bay, first thing they ask is like, how do you scale horizontally, or like, do you have a web server? And then like someone would come to me and says, oh, we have a 100x more scalable solution. And you ask them, how so? Oh, they say, oh, we just take 1,000 servers. Guys, this is not really scalable. Throwing a disproportionate number of resources at a problem is not a solution. So networking is exceptionally expensive. You have to package the data, you have to serialize it, you have to send it over the network, then you have to perform all of those operations in reverse order on the opposite end, and only then you can continue working with data. Just not having to pay those things, those penalties, means that SQLite by itself is many times better in a lot of use cases than Postgres or any other super well-funded database company out there.
I totally agree. This is a big subject, but maybe we could also like switch gears a little bit. I would like to talk more about USearch maybe, and because now AI is like hype. Maybe it's like a pejorative word, but it's pretty popular, right? Yes. And there's a lot of companies creating vector databases, for example, or vector searches, or all that stuff. And I was wondering how USearch fits into that, and what's your ambition and what's your goal with that? How you see the competition versus what you're building, and maybe.
I think that's the perfect segue, because quite recently, due to community requests, I've added SQLite integration for USearch. I wouldn't call it a full-fledged integration, but before that, what is USearch? USearch is a vector search engine, essentially meaning that you can have like a lot of vector entries, like high-dimensional arrays of numbers, and to search for them efficiently, you need some indexing data structure. So like we search through sets of strings or integers using binary search trees or hash tables, or hash maps, hash sets, whatever. Similarly, to search through large arrays of vectors and perform approximate nearest neighbor search, you would need this kind of data structure. This is, again, not my first vector search engine. This topic is very close to my heart, so much so that when I was building up our teams, implementing or optimizing an existing vector search engine was one of my interview questions. And myself, I've written 15 of them, more or less.
That's pretty cool.
So there are different approaches to implementing nearest neighbor search structures. The three commonly known ones would be KD trees, which stands for k-dimensional trees, locality-sensitive hashing, or LSH for short, and the last well-known family would be based on proximity graphs. So a graph is like a set of vertices and edges connecting them, so like a network. And proximity graphs would be networks of closed vectors that you link with each other, and then you traverse this network searching for the best matches for your candidate query. So in the family of proximity graphs, there's like two kinds of structures that are well known: NSW, and HNSW, the hierarchical navigable small world graphs. USearch implements the latter. It does so in C++11 to be very broadly compatible with other systems. And thanks to this, it's like practically the core of the index is one header file. It has bindings to, I assume, maybe like 10 programming languages, including C99 being ABI stable. Implementation in C++11, it has bindings to Python 3, JavaScript and TypeScript, Rust, Golang, Objective-C, Swift, C#. It has a few other bindings that are hard for me to remember, but the community is kind of also jumping in and adding support for like third-party stuff. This is the first-party support, by the way. So the CI, as you can imagine, to test and validate every single release is a nightmare.
But there is like a small detail I think we are forgetting to add. USearch is also like super fast, right? It's one,
yes.
if not the fastest,
maybe.
to my knowledge.
I think we didn't forget, it was obvious.
There are a few things that are true about C++, I would say, and maybe C as well. Those languages give you a lot of flexibility to write software. And you see this pattern oftentimes in software where people start implementing stuff, let's say in Python, and I do that a lot, and then they switch for like a more efficient native implementation. Right. But I tend to think C++ is not one language, or it's like more of a combination of different language features, and every expert or like senior developer selects his subset. Mm-hmm. And there are few things you can do combined, they result in exceptional software. Like if you know how to use CPU caches effectively, how to avoid memory allocations, heavy template metaprogramming, which affects the compile time negatively, but may help you with the runtime. And then the last, but definitely not the least, of the few things we do that maybe differentiates our software from most of it is we are ready to write assembly when we need to. Mm-hmm. So we write assembly for x86, for ARM, and for CUDA. Mm-hmm. We also write custom drivers for storage and networking, meaning that when we need to replace abstraction layers, there's nothing at which we will stop. Mm-hmm. No matter how long it takes to design it, if it's top performance, we're going to build it.
That's an awesome approach. And I remember during one of your talks, you were like doing this like analysis of system calls, right? For like a FICE, I think, implementation it was, or something. I'm not sure exactly, but you were seeing the calls and you like observed that there is some kind of like a bottleneck, right? And this led you to this idea that maybe the allocation is not optimal for like this graph creation. And that's pretty mind-blowing, I must say. This level of attention to detail and how you think and how you approach the problem.
Well, when you start doing it for the first time, first you read a lot of code. After that time, spent reading it, you may want to run it. You start profiling it. Profiling native code is very complicated, especially when the code bases are convoluted. So, for example, like the last couple of days, I was poking around PyTorch code base, and PyTorch is one of those examples of very convoluted code bases with a lot of abstraction layers.
High abstractions.
Yeah, so you either at the top layer or the bottom layer where you write kernels, but understanding how all the machinery in between works is really hard. Mm-hmm. That's why I believe in this very rare kind of software that can be short enough to understand and comprehend and maybe teach over a couple of hour-long course, but still performant, maybe state-of-the-art performant. Yeah. So one thing is to design a working piece of software. Another level of commitment is making the working piece of software elegant. The next level would be short. Mm-hmm. And then once it's short and elegant and working, the top tier of software would also be extremely performant. And we hope to get to this standard.
That's pretty amazing. When you were talking about that, it reminds me of this, recently Andrej Karpathy released this LLMC implementation, right? Yeah. And it's, I think, similar philosophy. Like there's more and more people trying to simplify things or reduce the number of abstractions, flatten them, or just see how we can improve things. And it seems like there's a good trend in that direction.
I totally agree.
Yeah, but I'm wondering, when we are talking about open source projects, it makes sense, but for a company, how sustainable it is to try to replace every bit and piece of of the stack in networking, for example?
Oh, that's a good question to which I may not have the answer. So there are some companies that have been particularly successful at commercializing open source that may not necessarily go in the aligned direction with the original author of the software itself. I think that's one of the big obstacles we have to solve as an industry, how we incentivize open software.
Right.
And the implications might be much wider than just the world of engineering and writing code. I noticed that, well, of course, science is becoming more computational. And when we look at all of those scientific domains, let's say biology, we have all those pharma companies who prefer to do all of the innovation behind the closed doors with a lot of patents, with constant legal battles. I think if we manage to solve this for IT, we may be able to later standardize it for other disciplines. And imagine the world where the pharma will be more like Wikipedia or Linux, where a lot of parties who often disagree and have very strong opinions still work together in a shared mission.
Right. Yeah, I agree. I wanted to maybe step back a little bit and return to, we have USearch,
Yes.
vector search, we have UStore, UForm. Could you maybe describe how those pieces fit together? For example, what is UForm and how it's like, what's the output of that? What's the input maybe? And
Of course.
if the output of one could be input to another one, or?
Of course. So today, of course, there are millions of applications that are built with different data processing technologies. But in reality, I think there are very few core pieces of infra that practically every application needs. One of that would be a storage layer. Another one would be an indexing layer to be able to fetch the relevant pieces of information quickly. Another one would be a semantic layer. And this is such a overloaded word, but that's what UForm is. And the last but not the least would be networking. So UCall is a networking library. It allows you to separate the server logic from the client. So yes, of course, we want to make portable software that can run on a phone, on a watch, on any IoT device, but sometimes, of course, you need to access remote information. You want to call a server that does certain work for you. That's where UCall comes in, where you delegate work from your client application to a server, sending oftentimes a JSON RPC request. Then on the other end of this pipeline, the server might be interested in like processing some information and giving you an intelligent response. Processing this information, it may end up working with a mixture of structured and unstructured data. Dealing with structured data is generally quite easy. We do a lot of if statements. A structured data would be like a document that is already parsed, like a JSON or an XML or an HTML tree. And what you would do with that, you would write those if statements, for loops, whatever, and build your business logic. But when you deal with unstructured data, you need some ideally universal form to represent all of this unstructured information before you can connect it to your logic pipelines. That's what UForm is, universal forms. We take images, we take text as the two original and like most commonly used modalities of data. That's the term the AI community loves, modality.
Multi-modal.
Yeah, multi-modal. So UForm is a family of pocket-sized multi-modal AI models that we are building for vision language domains. One of the features of those models is that they're very small. They can run on both small devices and the large ones. They are multi-modal, meaning they can deal with images, texts, and hopefully very soon video domain as well. They are capable of producing embeddings so that you can search through the semantics or like through a semantic space of those multimedia documents. But some of them are also generative. They can produce like a textual output or description of an image or answer questions about the visual domain. They are multilingual oftentimes. Not all of the models, sadly. It's like somewhat compute constrained in our case. being an open source movement. We don't always have the resources of some of the commercial entities, but we take a lot of pride in our international background, and we love how amazing all the different languages are. So some of our models are trained on a balanced data set, meaning equal representation of every language in a training set. Generally, this would constrain to like 20 languages or so. So let's say equal amount of content in English and Chinese, Russian and Arabic, German and French, Spanish and Portuguese, and like all kinds of other language pairs. So with these models, you can produce, let's say, an embedding that will allow you to navigate vast volumes of images and find similar ones. So let's say someone can just type in a query like 3 guys sitting in a room, in a pink room, and talking about technology. And even if you have billions or hundreds of billions of entries, with USearch, the vector search engine, you can navigate the embeddings of all those different images and video frames and textual documents and find the right one. And then the last but not the least, when you know the identifier of the document that you're interested in, you can fetch it from a storage system, pulling in the raw original and streaming it back to your user. That's where UStore comes in. So this is not an exhaustive list of the stuff that we've built over the last few years, but it felt very natural that we should start with open sourcing those 4 technologies.
And you also mentioned during your talks that you did applied some interesting techniques. For example, you reduced the number of dimensions, right?
Yeah.
And because of that, you can be faster and more memory efficient, if I'm not mistaken, and it will take less space to contain those information.
Sure.
That was pretty interesting, like mind blowing in a way, very low level.
We are not magicians. We cannot solve every problem in a computer, but sometimes we find ways around them. And one of the most obvious fundamental limitations in modern computers is the latency of the memory system. So when we talk about latency, we often think about the latency of accessing remote systems. Like you build a web app, and then it takes like 100 milliseconds to fetch an image from a remote server because the server is somewhere in a different country. And then you add a CDN, a content delivery network, to cache something nearby so that the latency drops, let's say, to 20 milliseconds or something like that. And the user doesn't feel the difference. In my case, at least the last few years, we operate at different level of latencies. It's not 20 milliseconds versus 100 milliseconds, but I can spend a week optimizing an operation that takes 10 nanoseconds for it to go as fast as like 5 nanoseconds. And the reaction that would generally come up is like, why the hell a person with a fairly high hourly rate would spend 7 days working on an operation that takes 10 nanoseconds and optimize it down to 5? Well, the answer is some of those operations are executed billions of times per second on tens of thousands, hundreds of thousands, maybe millions of machines worldwide. Actually, maybe even billions. So no matter how much time and effort you put in optimizing them, there is still a positive effect. And one of my favorite examples is my strings library. I don't know if you've seen that, guys.
Yeah, StringZilla.
Yes, that's it. So when we think about programming, every single language has like numerical types, like floating points or integers and that kind of stuff. So float and int is implemented in hardware. So the language just provides you an abstraction to call into the specific assembly instruction on the CPU side that takes those 8 bytes and those 8 bytes, and then the arithmetic logic unit does like all the complicated circuitry to shift the bytes, intersect them in different ways, and then give you the answer. The first non-trivial type that appears in every language or class or structure is a string. That's the first thing people implement in software. And I kid you not, even there's like so much space for optimization in every single ecosystem I've seen. So StringZilla was born about 5 years ago for a conference talk as a proof of statement that strings and software can be so much more efficient. And to make a point, I took the most basic thing every single programming language has, a string, and I optimized the hell out of it. So I took the seamed assembly, which is single instruction, multiple data. That's the kind of assembly instructions that kind of makes up maybe 90% of modern assembly, yet almost no modern compiler knows how to generate it correctly. And I rewrote all the relevant string operations with that. Now, even today, even 5 years after this talk, let's say benchmark StringZilla against libc, which is the C standard library, kind of the state of the art in that domain, out of the standard libraries. And for substring search, something as basic as that, even on ARM, which is in everyone's pocket, it's a few billion CPUs running on ARM. The difference between StringZilla and libc is 3.5x in throughput. So it's like 10 gigabytes per second versus 3.
And why do you think it is that? I mean, why people don't use those? Like, why don't they improve things? Or maybe it's like a psychological or a philosophical question here, but...
There's definitely a psychological and maybe economic issue here. Like, we definitely haven't structured incentives in our community properly. And that's an easy way to get into a flame war. I guess if you're into those, you should check out Twitter for FFmpeg and some of those discussions. So there's a fairly small pool of people who are ready to write assembly. Pure assembly is sometimes a steep learning curve. A much easier way to enter would be C intrinsics. Intrinsics are like practically a layer between C and assembly that looks like C, but in reality is kind of assembly. And aside from implementing the library in those, you have to provide a lot of good examples, documentation, and blog posts around how this works, how it's structured. So like even in StringZilla, for example, the README, the main README, not the only one, of the library is 64 kilobytes of text. So with diagrams, with code sections, with examples, and the source code is also very deeply documented in the C code base, in the Rust binding, in Swift binding, in Python binding, to encourage people to learn this stuff and contribute or maybe just fork it and re-implement some stuff that they think they can do better. So there is a complexity in learning this. There is a complexity in maintaining it. Sometimes I would hear statements like, this is too much effort. But to me, it feels like it's worth it. If strings are in every single programming language, in every single program, and if your library runs on every single CPU, we run on ARM, on x86, we run, and that's specialized assembly. We have serial, non-specialized code that can run on any other CPU, be it 32-bit, 64-bit, little endian, or big endian. We run on IBM mainframes from 20 years ago. To give you a perspective of how broad the coverage is, let's say USearch has bindings to 10 programming languages. One of them is Python. And then when you just take Python, you think the most cross-platform Python package would be NumPy. But then you check the binaries that NumPy ships. Being just a BLAS wrapper, they don't ship their own assembly. They cover 35 targets. StringZilla and SimSim, for example, another one of my libraries, it shipped 105 binaries just for Python alone on every single release. So there's a lot of room for improvement in our software pipelines, and I would definitely encourage everyone to check out the blogs of some of the other great engineers who write about this stuff.
Maybe last question, a bit a random question, and maybe still philosophical. When I approached you after your talk, I started talking about RISC-V.
Yes.
And this is my like a little big passion. I'm not super knowledgeable about RISC-V, but what I like about RISC-V is that promise of like applying open source principles to processors, to hardware in a way that you don't have to worry about legacy stuff like supporting legacy registers or like architectures, and you can in a way start from a clean state. And I just wanted to ask you your opinion or what do you think about that? What do you make of it?
I'm very excited about RISC-V, as you can imagine, assuming I was just mentioning like the potential impact of open source and what would happen if we apply the same principles in biology and pharma and the other domains. Hardware is another one of those. Today, we live in this oligopolies where we have just a couple of foundry companies, a couple of chip design companies, and a couple of chip design software companies that kind of control the whole pipeline. And it's not just about the dependency on those companies. I like their work. There are some amazing people working and running those companies, but it definitely constrains innovation. It constrains the ability to reason about the system. It negatively affects the security. RISC-V is a very interesting instruction set. It also has some of those SIMD instructions, which attracts people like me, who love to brag about how bad the compilers are and how good the assembly can be. I've seen just one library that is about to get support for native RISC-V vector extensions. It's called SIMD-UTF, another great library worth supporting and maintaining, not mine. It's by Daniel Emir and a few other great engineers. But yeah, RISC-V is absolutely amazing. I wish I had a server running on RISC-V so that I could prototype my software on it. We'll have to wait for a few years.
Because it seems that this would be perfect, right? Software optimization and hardware optimization at the same time, and it could it's in the middle.
But we have to just be very clear here that if you want to design hardware specific, if you want to co-design the hardware with the software, you would still not be able to do it on RISC-V directly. So you would probably need an FPGA to test the hardware kernels. And then you would probably over time plan the tape out process. And yeah, you may end up designing a new RISC-V feature and then tape it out as an extension of an open RISC-V core. So it will be a multi-year process.
Mm-hmm. Yeah, but it sounds very exciting.
Yeah. Definitely exciting, and a lot of space for people who love to think beyond abstractions.
Absolutely. Ash, thank you very much for joining us today for this amazing interview. We learned a lot. I love this kind of interviews, and good luck with your projects.
Very low level, but lots of information.
Yeah.
Thank you, guys. We have a lot of high-level stuff as well, and we are very excited about seeing more developers coming from JavaScript, TypeScript, Python, and other places. And just like with the rest of our ecosystem, for example, this week I'm porting UForm and other libraries to TypeScript and JavaScript, and we couldn't be more excited to see more developers adopting that.
Absolutely.
Maybe we can help.
Yeah, maybe we could help in a way.
Yeah, that would be amazing.
The magic of open source.
Yeah.
Thank you, Ash.
Thank you, guys.